Okay, you can start, Ivan.
Yeah, I think off we go. Good time of the day, everyone. This is Ivan from EPIC, the European Photonic Industry Consortium. And today you're watching the online technology meeting on photonics for wearables. Let me remind you that EPIC is the largest photonic industry association in the world that includes 800 members. And we're there to support our members with the technology consulting, market studies, and opportunities for networking and marketing, for mentorship, for recruiting, and for investment. Without further delay, I present you the agenda of today's meeting. We have 7 wonderful speakers from every level of the value chain in the production of wearables here. And the first speaker will be from CEA-Leti, will tell us about the 3.5 silicon QC lasers and photonic integrated circuits. We'll hear also from Rockley Photonics about a full-stack silicon photonics platform for wearables, and from TNO about the tissue optics Monte Carlo analysis for wearables. We have here in the room also MantiSpectra that will talk about the spectral sensors for consumer applications, and a new company Xpanceo that will present the low-dimensional materials for advanced biosensing applications. The EV group we'll talk about wafer bonding and enabling the micro LED displays revolution. And Sabic will talk about the resins in optical lenses. And with this, I would like to already announce the first speaker of today, but he's Bakir, the senior scientist of CEA-Leti, and he will open this meeting. Badhise, please, whenever you're ready.
Okay. One second, excuse me.
Yeah, but before you continue, you need to swap those screens again. Perfect. Yeah, so the floor is yours.
Everything is okay?
Yeah.
Okay, perfect.
Thanks.
Okay, thank you. Thank you, Ivan, for the introduction, and thanks to the organization for providing me the opportunity to present the work, the Leti work on in the field of silicon integration and miniaturization of mid-infrared devices for optical sensing application. When talking about chemical sensing or chemical sensors, we often come across keywords that are frequently mentioned, such as size, price, and performances. And when we have to develop a solution, an efficient and affordable solution, we have to combine these 3 features and usually find the trade-off between them. Excuse me, I have a problem with the presentation. Okay, here you can see, for instance, a low-cost photoacoustic CO2 sensor developed by Infineon. And this solution is mainly dedicated for indoor air quality monitoring and defined application in smart IoT devices, for instance. In that case, the limit of detection is relatively high, 400 ppm, but the footprint is low, half a square centimeter typically. And in the other side here, you can see a FTIR, a huge FTIR equipment, which is a part of a testing lab solution. It allows for gas and chemicals detection far below the ppm, but in a laboratory with well-controlled ambient condition. So in both cases, we use the same principle of operation, a black body source and a photoacoustic cells, but we have here two opposites, a testing lab solution with ultra-low detection limits, and here a low-cost, low-footprint solution with moderate performances. Our development on silicon here at CEA-Leti aims to combine both advantages thanks to a finely tuned device and silicon integration schemes. In a work proposed in a couple of years ago, we proposed the concept of fully integrated multi-gas sensors on silicon. Here I present a multi-gas sensor module, but the concept can be extended to biomolecular sensing and wearable devices. The big building blocks are the same in both cases. Here you can see a module, which is a dummy demonstrator actually, which combines lasers, photonic integrated circuits, and the photoacoustic cell. It gives us a rough idea of the total footprint when all the devices are assembled to form a module or a system. This module combines an array of quantum cascade lasers on silicon, which act as a multi-gas detection. Here, a photonic integrated circuit, which is a beam combiner. The idea here is to replace costly and fragile discrete optics. And all the lasers, thanks to the beam combiner, are combined in a single output, which address a single gas sensing cell. Here, in that case, it's a photoacoustic detector with MEMS microphone. Here, the idea is to replace bulky multipass cells or single-pass cell. So here now, I propose to present you all the basic building blocks developed at CEA-Leti. And here you can see the laboratory gas measurement of the detection, the limit of detection we obtained for our mini photoacoustic cell, which has a footprint of 3 by 3 millimeter. And the typical value we obtain is, in terms of limit of detection, is below the ppm with a laser output power of 1 milliwatt. And as you can see here, in the case of nitrogen oxide, in nitrogen, we obtain a limit of detection around 50 ppb. The important message in the photoacoustic cell is that the signal, the recorded signal by the microphone is virtually proportional to the square root of the volume of the cavity. So the performance scale with volume reduction in our case. Here you can see some results we obtained for the mid-infrared photonic integrated circuits, the results on MUX multiplexer and demultiplexer. We use here the silicon germanium mid-infrared platform because of in order to reduce typically the absorption we have when we use common dielectrics such as silicon dioxide. And the result we obtain for in the 3 to 8 micron band, we obtain very low propagation losses. And we demonstrate a combiner with 35 inputs. Here you can see with low insertion losses and a crosstalk below 12 dB. Concerning the band around 10, 12 microns, the propagation loss, we have a pure germanium core and silicon germanium cladding, and the propagation losses are a little bit higher, 5 dB per centimeter, but we expect in the short term to reduce these propagation losses down to 2 dB by modifying a little bit the design and the epigrowth condition also of the germanium. So concerning the heterogeneous integration on silicon of quantum cascade lasers, we have a specific design here. In that case, we have a heterostructure bonded on the silicon wafer, thanks to silicon dioxide. It's a silicon dioxide bonding technology. And we have a 3-5 active waveguide here, and a grating on the top, which is covered by a metallic mirror. It's a plasmonic DFB. And on both sides, you can see the electrodes for the electrical injection. Here, the particularity of the design is that the top electrode serves not only for the electrical injection, but also for the plasmonic behavior of the laser. Concerning the process flow, it's relatively simple. We use the full wafer bonding technology, and then we remove the substrates, such as an active region, the heterostructure, with a total height of, let's say, in between 5 and 10 micron remain on the silicon substrate. Then we etch the DFB laser, the 3-5 active waveguide. We passivate the heterostructure, and then we open the passivation in order for the metal deposition, and we end up with here the picture of the final fabricated device. In terms of technology, here we achieve wafer bonding. Here you can see for 4-inch and 2-inch. We also have the die-to-wafer technology, and we have a bonding yield of about higher, let's say, than 95%. You can see here the acoustic images of the interface, the bonding interface, and you can see here the small bubble corresponding to the unbonded region of the 3-5. So it's very low. Here you have the pictures, the ACM pictures of the DFB grating here, and we develop a specific process in order to have for each wafer the same edge depth. Here a picture of the deep ridge of the QCL waveguide here, and after metallization, a picture of the final fabricated devices. So we obtain here, you can see a typical laser, we obtain around 7.4 micron. We obtain a very high yield in MEMS compatible process environments, but the performance still has to be improved. We have some issues regarding the cladding absorption, some self-heating. Also, we have solution to improve performances with some heatsink, the integration of heatsink during the process, and we still have to improve the metallization also. So in our roadmap, we expect also to combine the silicon waveguides and also the 3-5 lasers in a single platform, 200mm platform. And we have the starting point of development is our experience on telecom lasers, the mid-infrared. Here you can see, for example, a laser operating at 1.55 microns, which is coupled to a silicon waveguide. Here, the 3-5 waveguide only acts as an amplifier here, and here the optical modes travel in between the 3-5 and the silicon thanks to adiabatic tapers, and the cavity here is defined in the silicon waveguide platform, and thanks to the imbalance in between the mirror reflectivity, we have an unidirectional emission, which is outcoupled to a fiber thanks to surface grating coupler here. Here I present the DBR laser, but the concept can be extended to DFB laser, to ring laser. A lot of geometry are available, and we have plenty of room in terms of development, which is a hybrid platform. In that case, we obtain very nice lasers with low threshold. It's CW in that case, and a sine mode suppression ratio above 55 dB. So we wanted to develop here the same technology, but at 4.5 microns. In that case, we have to develop a specific waveguide platform with a buried oxide, which is a little bit modified. We have to play with the absorption of the low index contrast here cladding. So we add a silicon nitride, but we can also add if we want to extend the operability up to 8 or 10 micron, instead of silicon nitride, we can use chalcogenide here. So we develop different platform here in order to couple waveguides and to limit the propagation losses here. So we demonstrate here with the simulation that even if we operate in TM00, we can couple the mode to a silicon waveguide. So for the moment here, the waveguide is already fabricated, and we have to bond the 3.5 and to demonstrate at 4.5 the lasers. So our technological roadmap for the short medium term include the co-integration of QCL and photonic integrated circuits on the same platform, 200 and 300 millimeter platforms. And we are looking also, we are developing solution in order to reduce again the photoacoustic cell by one order of magnitudes. And the idea is to reduce the footprint by a factor of 10, in between 5 and 10 at the end. This is the end of my talk. Thank you very much for your attention.
Yeah, thank you for the talk, Badhise. That was very exciting. So let me remind you that today after each talk, so we have time for several questions from the audience. So just please use the button for a raise hand at the bottom of your screen, and I pass you the word. So do we already have some question for Badhise? Let me start myself, in fact. I'll give you the typical EPIC question, because now in the room you have the professionals from every level of industry. So you have some technology enablers, you have several, I can see, system integrators that could use your chip in a more sophisticated system. So yeah, could you say maybe what you can do for the other members of EPIC and what they could do to help you develop this?
Okay, so our model, yes, regarding yes, we are open to collaborate, bilateral collaboration with industrial. We have this model at Leti. We are developing actually this solution for different players, starting from gas sensing to biomolecule sensing for glucose monitoring, for instance. So we are open to collaborate with other industrial partners, but we are also open to collaborate in the framework of European project also. So this is the model we have at CEA-Leti. So we have industrial partners, but we have also in a bilateral framework, I would say, and we are also open for collaboration in the framework of European projects.
Okay, thank you. Anyone else has a question? Wilfred, did you raise a hand or not?
Yes, I did. Very interesting. I like your heterogeneous QCL approach on silicon. This is pretty cool. Can you go to longer wavelengths as well? And since you have plasmonic waveguides, what is your loss typically?
The losses for the waveguide, yes. In between for the high index contrast platform or for the silicon germanium platform?
Nope. In general, for this, no. When you make a QCL with a gold plasmonic waveguide.
The plasmonic one, yes. For the laser, for the first platform, yes. The losses, everything combined is not a buried laser. Okay, so everything combined, I'm in between. I would say 8 and 12 per centimeter in terms of losses to be that have to be compensated. Say we need, I would say, yes. More gain than, but yes, with external laser we'll obtain, and with other technology we'll obtain better performances, but we target applications with moderate output powers.
I see.
We are targeting it's large scale, low cost production of lasers. It's not the same.
And can you go to longer wavelengths around 10, 11 microns as well, or?
Yes, we demonstrated 8.5, 9. So we have to modify in order to go above, beyond 10 microns. We need to adapt the QCL design and to provide more gain, because this architecture works well for, let's say, the 4 to 8 micron bands, but we have to change a little bit the architecture to go beyond 10 microns. Yeah.
Okay, oh, it's already pretty cool.
We have issues on the propagation losses.
Yeah. Thank you very much.
Welcome.
Another question from Andrei from DeepLight.
Yeah. Hello, nice talk, nice results. How do you deal with cooling of your diet?
Okay. Yes, good question. We have we have a Peltier module, but we operate most of the time in the pulse regime. So we optimize the electronics. So we characterize our lasers and we optimize the pulse condition, the duty cycle, and the pulse duration in order to prevent from detrimental heating. But we always have heating. And the other option is to contact, for example, the bottom or the top contact to the substrate. So you connect to the substrate and you can improve the laser performance in general because we have a good dissipation with the silicon substrate, better than indium phosphide substrate.
Yeah, nice. Thank you. Thank you.
Welcome.
And I see that there is another question in the chat from Julian from Coherent. Would you like to ask it yourself?
Yes, thanks. Yeah, indeed, very nice talk. I had a question about the DFB, the plasmonic DFB. How do you fabricate it? Are you using e-beam lithography or are you using another technique?
Yeah, good question. We developed a specific deep UV lithography, and the difficulty we have is to deal with the topology of the bonding, since we have a 3.5 wafer and the 200 millimeter wafer and the 3-inch or 4-inch wafer. So we have some topology and we have some difference in terms of thicknesses. And we developed a very specific process with ASML in order to use the deep UV lithography and obtain the very nice resolution. Because the lithography, the e-beam lithography, we have e-beam lithography. Even if we have an industrial e-beam lithography, it's not, let's say, it's good for demonstration, but in terms of throughput, it's too low. So it's deep UV lithography.
Okay, thank you.
All right. So now, if there is no more questions, anyone else? Yeah, if not, let's we think Badhise again, and yeah, please keep in mind that yeah, you're welcome, always welcome to reach out to him after this talk if you'd like to work with CEA-Leti, correct?
Yes.
And also you can reach out to me, so I can put you in contact with Badhise. We always foster the communication between our members.
At the end of the talk, we have also the business developer at Leti. And his name is mentioned at the end of the talk, and I think that you will send all the slides.
Right. Yeah, the slides will be available on the event page. Yeah. So yeah, feel free to reach out to CEA-Leti. And with this, I'd like to invite another EPIC member, Rockley Photonics, and Casimir Wierzynski, the senior vice president of Rockley, will tell us about the full stack silicon photonics platform for wearables. Casimir, good morning.
Hi, good morning, everyone. Let me start sharing here.
Whenever you're ready. Yeah, the floor is yours.
Okay, great. Thank you very much. So yes, I'm Casimir Wierzynski. People call me Kaz for short. I am not actually a silicon photonics engineer or designer. I'm actually, I run the AI and software groups at Rockley Photonics. So please don't ask me hard questions about fabrication. I'm actually going to tell you about the full stack platform that we're building for wearables, starting from silicon photonics, and we're going to go all the way up the stack to algorithms and human applications. So just a very quick blurb about Rockley. One of the things that I think differentiates us as a company is that we do work across the entire stack of multiple technologies. So, clearly we work in photonic and electronic ICs, but we also put these into modules. We use these modules in devices that we get into the measurement science, and we analyze the data that come out of these modules. and develop AI and various ML-based analytics around these data. And we also have a very large and growing IP portfolio across all of these areas. I am a bit preaching to the crowd here, since this is a gathering on wearables, but just to kind of set the context here about why this is important, why I think we're all here. From our point of view, two trends that we can see pretty clearly. One is around healthy people and consumers who want to monitor their health, who want to quantify their health, who are comfortable with technology and want to know everything about themselves. And to the extent that they need to be monitored, they want that to be in a friendly home context and not in a hospital, let's say. So that's kind of the healthy crowd. There's also a very large trend around chronic conditions, and those chronic conditions are very expensive. Health systems are strained by these, and it's often useful in treating those conditions, not just to get point measurements of how the patient is doing, every 6 months, but the more continuous kind of information you can get about these patients, the better you can treat them. So in the context of those two trends, there are a number of biomarkers, let's say, that people would want to measure from either healthy humans or humans with chronic conditions. These are things like their heart rate, their hydration levels, their body temperature, alcohol, maybe other chemicals in the blood, lactic acid, glucose, and so on. And there are a number of existing ways of doing this. There are machines that you can use in the clinic, and maybe some of them you can take home, and some of them maybe you prick your finger. They all have different modalities for how you use them. Some of them are invasive in terms of having to penetrate your skin. It's a very large collection of devices that you would need to monitor all these kinds of things. Our approach is, how much can we do in a wearable form factor and in a non-invasive way? Because if you put those two things together, then suddenly you open up a whole set of use cases around continuous measurement and being able to do things that are that kind of bring health much closer to people's actual lifestyles. So our approach has been, what can we really push this wearable form factor as hard as possible and still get specific information about people's blood chemistry? And we fall back to very classic chemical analysis techniques for figuring out blood chemistry. So spectroscopy is a very powerful and well-known way for chemists over the years to identify both the identity and the concentration of various chemicals in various contexts. So for us, the shortwave infrared region is very interesting because, as you can see from this absorbance diagram here of different substances, especially if you look in this area from 2000 to 2400 nanometers, you see very distinctive absorbance curves for biologically interesting molecules like glucose, lactate, ethanol, creatinine, things like that. So our overall approach is a spectroscopic approach. And in the upper right, you can see a kind of a subsection, a cross-section of human skin. If you can get slightly through the epidermis, now you have access to the beginnings of blood vessels where, or tissues where these chemicals can diffuse into. And if you can deliver light and then read out the light from those regions, you can make interesting inferences about blood chemistry. So that's the SWIR spectroscopy. Now, how do you measure this spectrum? And there have been, a spectroscopy is all about getting enough light to where you want it of the right wavelength so that you can then, measure the right quantity coming back. LEDs have been one way of doing this over the years. I think one of the drawbacks of LEDs is that, for a given source, you actually have a fairly wide set of wavelengths that come out of a single LED. So our approach is actually to say, let's build up a spectrum out of up to 100 wavelengths of lasers on a single chip. So you can then light up each one of these lasers individually and get a very precise in wavelength delivery of light and therefore measurement of what the absorbance spectrum is at that wavelength. Now, we're going to go slightly up the stack here. So, having developed a PIC that's capable of delivering and measuring all of this light, we now need to embed all of this into the right electronics and the right mechanical engineering to support this activity, battery and so on. So it's the wearable space is a very demanding form factor for trying to integrate all of the photonics and electronics that you want. So here you can see an exploded view of what we call our bioptics band, which is initially targeting the biomarkers of hydration and body temperature through SWIR. And then we have additional biomarkers that we can measure through traditional PPG-based measurements using an LED. So if you put that all together, you have an interesting initial foray into this space of measuring some biomarkers relating to homeostasis. Now, if we move up one step further in the stack, you realize that if you just have a bunch of people wearing something on their wrist, even if it's very complicated and fancy, you need access to those data. That's useless without some kind of organized way of moving data on and off the device and making those data available to developers of applications who want to make interesting inferences around those data, as well as integration into the systems that consume those data and consume those inferences. So you'd like to be able to connect things to, systems of people conducting clinical studies or remote monitoring of subjects. So our overall architecture is that we've also developed a mobile application, this thing called Connect Edge on the left, and it has various APIs so that if you have your own specific mobile app for a particular use case, like let's say glucose monitoring, it can talk with our app. So our app handles all of the data connectivity between the band and a mobile device. And now this mobile device has uses a bunch of APIs we've developed to push data to a cloud, our Bioptics cloud. And then that cloud offers further APIs that other developers can use. I'm kind of going from left to right here, to quickly build up their own applications or integrations into these data streams. So a very quick example of an application you can build fairly easily with our APIs is if you just wanted to look at the raw data coming off the device in a data lake. On the left, there's an absorbance spectrum here. I mean, I don't want to get too lost in the details of these graphs, but we're graphing absorbance spectra, or on the right, we have accelerometer data coming off the band. These are, applications on the web that would take, I don't know, probably just a few hours for someone versed in something like Streamlit to build. So we really want to make, I think, a key to this, having a platform like this be successful, is not just the silicon photonics, which is obviously very important, but being able to go all the way up to the delivery of the data and the insights themselves. I want to run through, I keep going up the stack now, because now once you have the data, you want to learn something about somebody's health, right? You want to start building applications and algorithms around these data. So we've initially looked at a couple of core aspects of human homeostasis, which is being able to maintain a constant temperature and being able to maintain hydration. Those are both, like, hydration is an interesting one, specifically in the area of elder care, where you have, you may have some patients who, because of dementia or various other reasons, don't drink enough and actually end up dehydrated and in emergency rooms because they weren't drinking enough water. So we'd like to be able to measure that non-invasively and continuously. So before I show data, I want to show a little bit about how we collect it and some of the experiments that we run at Rockley. So one way before you get to human testing, is that you can, in a very controlled setting, kind of build an artificial block of skin out of gelatin powder and some fat and some water. And now you can kind of construct these little, kind of a very controlled, what we call tissue phantoms, so kind of artificial blocks of tissue at very controlled hydration levels and very controlled temperature readings. And then we can use those to build up models of these two biomarkers. And when we do that for temperature and hydration, you can see you can get a very nice, using partial least squares, which is a very classic chemometric analysis technique for spectroscopic data. You can get a very nice fit of body temperature and hydration using SWIR spectroscopy on a wearable. And of course, then the question is, how well does it do in humans? Because humans are not a single block of collagen and fat. They have hair, they have varying thicknesses of skin, they wear their watch in different ways, so there's all kinds of extra variability there. When we did that with thermometers, so we conduct these studies in our facilities in Irvine, where we make people wear, well, we don't make them, subjects volunteer to ingest a pill that measures their core body temperature and transmits it through Bluetooth. So we have a very good ground truth measurement. And against that, we calibrate our SWIR measurements. And you can see from this graph here, our points are the blue points. So our measurements relative to other reference devices are track very closely, I would say. And then finally, for hydration, a similarly positive result where we can build a classifier to say, is this cohort of people, are they in the non-dehydrated, or have they transitioned into kind of a dehydrated state? And we can do that with fairly high sensitivity and specificity. The way we dehydrate them is through exercise. So we have them basically riding on a bicycle in a very hot room for a few hours, and they lose up to 2% of their body weight as they do this, and we can track through the shift in their SWIR spectra, we can track how hydrated or dehydrated they are. So in conclusion, I think we've shown, kind of by pushing through the entire stack, I think we've proven out that SWIR can work in a wearable form factor to the point where you're getting biomarkers out that are clinically useful. And so that's why we're kind of encouraged by this full stack approach. We've also tried to make this platform easy for either software developers to use these biomarkers or other researchers to come in and think about how would they develop a completely novel biomarker. So using these spectra to correlate against something else, how can we make that kind of study easier for them? And so to anticipate Ivan's question about, the kind of help we could get from this group, we're always looking for folks who would want an integrated device like this into either some existing health application, or if they wanted to develop a novel biomarker of their own, for some disease state that we don't know about, we would love to collaborate with them on kind of a data science level to help them put these into the field on the wrist of people, do a study, help develop the model and serve the model at scale to their users. So with that, I'll take questions, and thank you very much for having me.
Thank you, Casimir. Indeed, you anticipated my question already. So let's see if there's any more questions in the room. Please raise your hand. And yeah, okay. Daniela from ITP.
Yes, hello. It's very interesting what we saw, what we could hear. My question is, are all those sensors validated for the medical sector?
Are you talking about like through the FDA or CE marks or things like that?
I mean, all those solutions you were presenting, are these sensors for, let's say, these key vital signs already validated? Because for the medical sector, this is quite a demanding process. This is why I'm asking.
Right. So we are not yet. So they are for the kind of the health and wellness space so far. and we are going through the process now of getting them through the validation that you talk about for medical uses. Yes, but not yet.
Yeah, it's great. Yes. Excellent. Yeah, we are providing or developing different solutions for also for medical sector, but mainly sensors integrated into textile materials, into flexible materials.
Cool. That's interesting.
Yeah, indeed.
Maybe they can work together.
Yes, I think so. I will keep and save your contact data. Absolutely. That's interesting.
Likewise. Thank you.
Indeed, that will be a great result already of this meeting if two of you get in touch. So let's see if there is more partners to join. Anyone else interested to try the Rockley photonics technology or to add up to it? I'm wondering, actually, Casimir, is there any roadmap for when are we going to see your product on the market?
I can't speak to that. I'll put you in touch with the right people, but yeah.
Okay, fair enough. Andrew from DeepLight?
One question, if you can disclose. So what platform is it? Silicon nitride? And like which foundries are you using? So is it in-house fabricated devices?
Yeah. So again, like I'm not the right person for the photonics questions, but I'm pleased. Let's get together after meeting. Happy to answer that. Yeah.
Okay. Thanks.
Yeah. I'm sure there's a lot of other people interested in the hardware part here. Yoshiaki from Sumitomo.
Hello. Thank you for the interest presentation. And I'd ask in aspect of the optical devices, the detection of 2 micron range, SWIR range, SWIR, the emitter will be LED, as you mentioned. Is that right, understand?
I'm sorry, could you repeat the last part of your question? I'm not quite sure.
So the emitter, the light source is LED. Is that right?
The light source is laser.
A laser. And what could be the detector for the 2 micron range? I don't think both silicon or even indium gallium arsenide cannot detect in that 2 micron range.
Again, like I'm probably not the right person for the silicon photonics question, so I'd be happy to point you to the right person at Rockley for that. Yeah.
Oh, okay. Sometimes I'd like to ask someone to you again. Thank you.
Sure. Okay. Yeah.
Yeah, fair question. So yeah, please feel free to reach out to me also. I can put you in contact with the colleagues of Casimir later.
Okay.
But Chaim from Now Capital.
Yeah, sorry, just one quick question. I saw that one of the items you listed that could potentially be tracked is non-invasive glucose monitoring. Have you already been able to successfully put that into a piece of hardware? Thank you.
Yeah, I can't speak to that development in this setting, but please follow up with me separately and we can have a conversation.
Fantastic. Thank you so much.
Yeah.
All right. Sounds like another follow-up. Anyone else? If not, yeah, I suggest we thank Casimir again for this very inspiring talk, and looking forward to hear more from Rockley in the future. And the next speaker of today is Vincent Zoutenbier, scientific specialist from TNO, and he will talk about the tissue optics Monte Carlo analysis for wearables. Vincent?
Thank you.
Yeah, are you ready?
Yes, sorry, I'm pulling up the share screen here. And you should see a shared screen.
Yeah, the floor is yours.
Great, thank you very much. Thank you for hosting and inviting us to give a talk today. My name is Vincent Zoutenbier. I am a scientist in the optics department technically, but also in the medical photonics group. We're in Delft in the Netherlands at TNO. So I don't know if it's widely known about TNO, so I'll just kind of give a little bit of background about that. It's a law-mandated institution that does R&D with a few themes, including sustainable society, healthy living, safe and secure society, and digital society. This kind of wearable optics, that falls into a lot of these categories. And so we have a group here that's working on in this space. We can actually take medical photonic devices from an idea all the way to clinic. We have a lot of hardware experts. We have a lot of analysis and image science experts along the way that we work with. So it's a very interesting space to be able to work in, and work with, because we are also always looking for partners to work with on new projects as well. So today I'll be talking about TOMCA, what we abbreviate as TOMCA, which is tissue optics Monte Carlo analysis. As you'll see, what it does is it takes millions of individual virtual photons and puts them through a virtual tissue, and then allows us to analyze the signals that would come out of such a device when we're building something. So I just wanted to seed a couple questions ahead of time. The kinds of things that this analysis can give you the answers to are things that are very specific, such as how much does placement error affect measurements? For example, putting it on a blood vessel or just off a blood vessel, that can be very sensitive. So that's something that we're looking, that we're able to build up, for example, in this analysis, but also very general things like how robust is my measurement device to a diverse population group, whether that's BMI, age, or skin color. So how we do this, how our system works is that we start with an idea of what a real tissue is. And so we say, okay, well, there's this biomarker that we'd like to be able to measure. And we think about what does that tissue all include? What are the optical properties and what are the materials involved? So for example, for skin here, we have the epidermis, which has different optical properties than the dermis underneath it, and the blood vessels that we may want in between, or in the lower fat layers. So we think about the distribution of those layers, and we try to understand that as much as we can so that we can model it. We'll then build a virtual model of it, where we are programming in the mu A, the absorption, mu S, the scattering coefficients, G, direction of scatter, if you will, and the index of refraction. And at every point in a virtual piece of tissue, a box, a matrix, literally in our code. And then we can add light sources in any geometry that we're looking for. It could be a laser, for example, like we heard from the last speaker, or LEDs. And then detectors as well. We can place those on the top, or we can just do a full bulk simulation and see where light is going through. And then this tissue, what the beauty of it is that because it's all virtual, you can change the properties very easily. And we have models that can change that tissue as a function of age or sex or skin color. And so we're really able to create an entire model that creates a diverse population. The way that we do that is by changing not only the geometry of the tissue, but also the optical properties of it. And so here you see that we have a few, we have kind of the engine equation, which is just a linear combination of each of the constituent absorbers in the case of evaluating the absorption, where we have the first two are the oxy and deoxy spectrum of blood. Then you have water, melism, just like we saw similar to the Rockley, but this is all in silica here at this point. And so we take all of the components and we have all of their spectra, and then we're evaluating them for the LED, or for the wavelengths of interest. And then that creates an effective mu A that gets put into the simulation, and we can change that with wavelength or any of these parameters as we go. So with the optical properties evaluated, we then can start pushing light through. I'm showing you here just a picture of what a model might look like, where we have all of the different layers of skin that light can propagate through. I have a little cartoon of a flashlight up top where light is getting injected. It can then go through and maybe interact with that blood vessel there, which is in the fat layer down below the dermis. So we go from this model to some actual images here. This is flux through the tissue. And so you see it in a couple of cases here. I'll walk you through them. This first one up here in the top left, that is a simulation of skin with a blood vessel there on in the center of that image. So at 532, you can see light comes in and it gets absorbed pretty quickly. You can compare that with the image just to its right. I don't know if I have a pointer. Oh, yeah, laser pointer, great. So here you can see that there's a little bit of shadowing from 532, the light coming in from the source, but a lot of it gets absorbed before it gets to the blood vessel. That's different than here with the red light, where the light is not getting absorbed, but it gets scattered a lot more before being absorbed or going outside of the volume. And so that's with an offset light source. We can also put the light source directly on top of it, and then you can see a beautiful shadow being made by the blood vessel where there's high absorption here, or there's some absorption and scattering going on over here. So with these kinds of volumes, we're also able to create a detector at the top surface here. So for each of these 4 tissues, we've put a detector at the top surface and plotted that profile. And down here, you can see those profiles plotted. So you see for the 2 green cases, you see that there's some reflections coming out of the skin, some light that's getting scattered back up at 532, and they're quite low because there's a lot of absorption. With higher scattering but lower absorption, you have the light from the red LEDs coming out, and you can see that when you're directly on top of the blood vessel, there's a lot more scattering than when you're next to it. But interestingly, you can see over here that there's an extra bump, and that's where this red laser, or this red source over here, is actually interacting with the blood vessel and causing more light to come up into the surface there. So that's what that bump represents. So this really lets us pick apart the tissue and make sure that we're understanding where our signals are coming from, for example. And so in the previous image, that was all of the light at once, the flux going through it. This, on the other hand, is just the photons that make it to a specific location. So from this light source, it goes 4 millimeters, and we're probing just this dermal, the layers in the dermis. And then if we move that detector further away, we can see that we're going deeper down into the subcutaneous fat, and then we can start to measure some of the optical properties down here to be able to measure the biomarkers that we're looking for. So this really gives a deep understanding of what's going on and gives us insight also into the limitations of the sensing that we're doing. So we're working on these Monte Carlo simulations to improve a lot of current technologies, make sure that they work on a full diverse population, that we're also getting a good handle on where our sources of errors are and estimating what they are. We're also working on some new applications and new devices. This is something that we're also looking for from new partners, what we can simulate, where we're looking to move in the future. We have a pretty nice framework that we use in order to move products towards completion, towards TRL, the higher TRL numbers. We start with a concept. That's something that could come from in-house, that could also come from a partner, where we identify the biomarker and its interactions with light. We then build up our model. In some cases, very complicated cases, we'll actually use machine learning to help sort through the information coming out of the models to actually pick the sensor geometry. Maybe the machine learning algorithm can tell us what wavelengths we're using and what detectors, where we put our detectors. We can then develop hardware based on that. We can validate it in tissue phantoms that we're able to build. We can make layered phantoms that are very stable. And we also have capabilities of putting controlled blood flow through, and we can change the oxygenation of those blood flows. So we can really do some very precise work on validation before it gets to clinical trials, which is the final phase of our process. And so we have a capability in helping with lots of these steps, actually all of these steps. So that does take us to the end of my talk. Happy to talk through any questions, if anybody has any.
Yeah, wonderful talk. Thank you, Vincent. I'm sure there will be questions, maybe already from Casimir from the previous talk. I guess it's a very interesting area for him, but also anyone else has a question? Okay, Andrew, would you like?
Yeah, I really like this topic, so sorry for all my questions. This placement of sensor. So you mentioned like few millimeters, but thinking about how it's like possible like to place with this precision, it's really like tight tolerance. So
Yeah.
is it like realistic values? Or how it works?
So this is something that we're actively working on, trying to understand how much that placement, how much we can reliably do placement on skin for some sensors that we're also developing. And the Monte Carlo simulations are helping us understand the sources of error that could come from that. Yeah, exactly. How much do we need? How well do you need a nurse or a person to be able to place it, and how much can it move and still get reliable information out of it? So that's something that we're still extracting data from and understanding ourselves. But this is definitely helping the Monte Carlo simulations. You can see right here that you have the same peak in both cases, but it just changes in amplitude. So can you still extract information from this peak just like this one?
So the question is, what it should be, 1 millimeter or 10 millimeters?
The placement accuracy?
Yes.
I think it depends on the biomarker. How sensitive. It really depends on the biomarker. How well your signal to noise is for the specific thing that you're measuring within the spectrum.
Thanks.
Any more questions? Okay, Tom Harvey from CPI.
Hi there, Vincent. How you doing? I had a question about the Monte Carlo simulation method itself. So I do recall this method, I think. Do you writing your own software for this, or the method is available in some commercial packages as well, if I remember correctly? Just can you give us an idea of the complexity of implementing this type of modeling, and what happens if you have more than one blood vessel, for example, or you're interested in the effect of hair follicles, blood vessels, and kind of multiple scattering centers. So I know you've shown a very straightforward example for the purposes of illustration, but clearly it can get quite complicated, I would imagine, with the model if you're dealing with quite a few different features.
Yeah. Okay. So good question. There are some packages available. We've put a lot of effort into building on top of some existing packages so that they have the full capability that we need in order to do these quite nicely. And so specifically for the second part of your question there, the more complicated your geometry, of course, the more light will bounce around, and you'll have to evaluate changes in index of refraction or interfaces. Those are quite important in the modeling process. And so we have been developing methods to speed that up, and that's where there's a lot of uniqueness in what we're working on. We've been working on speeding up the process of simulations so that we can have more complicated geometries, including, for example, multiple blood vessels or more realistic geometries to the blood vessels. Because what we're looking at here is great for a phantom validation, but when we get to clinical trials, we need to know whether it's the same.
Thank you.
Okay, I hope that answers your question. So maybe just can you repeat again in what kind of frameworks you would be able to work with other EPIC members, and what would be the points of interest for you?
Sure, and actually I might even call on Michiel Olderwald here. Would you like to talk here?
Yeah,
he's one of our business developers.
Yeah, so Michiel Olderwald here. You can find me on the website of TNO, also my email address. So it's michiel.olderwald@tno.nl. So we collaborate with private partners, and that's actually what we're there for. So we want to help private partners, industrial partners, to get their technologies into the market. That's the role of TNO. And we have different ways of collaborating, and depends a little on whether it's really business to business work that can be done easily, or that we're really developing new knowledge. So sometimes we also can use additional budgets to match in-kind contributions and private contributions of a company together in a project that can maybe add 50% of subsidy to that, and then do some more research type of work that we can use both. So we can use it for new work in the future, and also the partner can use it for their own applications. So please contact me if you have any questions, or if you're interested to know more about this and what we can do.
Okay, thank you, Mikael. And thanks, Vincent, again for the talk. With this, I'd like to call the next speaker, Kelly Hakel, the Operations Director from MantiSpectra. And Kelly will talk about the spectral revolution and spectral sensors for the consumer applications.
Hello, thank you for the introduction. Can you hear me and see the screen?
Yes.
It's supposed to be black, so that's okay. Okay, so let me minimize this so that it works. So imagine you're walking in the supermarket and you can directly pick the fruits or the veggies with the best taste without trying them. Or you can extend the abilities of your smartwatch to track your well-being in an even more careful way. Or you're a police officer and you can determine in real time if this powder that you see here is legal or illegal. That sounds like sci-fi, right? But let me tell you this, we can already do this because we have developed a technology to start a spectral revolution. So my name is Kelly Hakel, I'm the COO of MantiSpectra. And we are a spin-off from the Eindhoven University of Technology. So we're also located in the Netherlands. And in order to show you what our technology can do, I want to highlight this application, because currently we see that there is a problem with quality control. Quality control is inefficient. What you need to do now is, for example, food companies, they take a sample, they send it to an external lab, and they do perform chemical tests, and then it's coming back. And this is taking quite a while. So what you would like to do is you want to measure in real time, in a portable manner. And then you want to measure and take action along the full production line, for example. So you have the incoming goods with the raw materials, you want to measure with a probe during the production, and you want to check the quality of the goods before you send them, before you ship your final product. So with our technology, which is a patented chip sense technology, we have a photonic sensor that is integrated on a chip, and we make use of near-infrared light. So we already heard a bit in the previous talks what you can do with spectral sensing, and that you can measure the material properties. And we are doing that in the near-infrared range. So what we have is a unique based chip solution, as you can see here on the left, and we combine the selective detectors with machine learning. So when you do this, you can quantify and classify material properties using light. And then you can do that by using the spectral fingerprint, as you see here. So we can all do this because we make use of semiconductor integration. On one wafer, we can already fabricate thousands of chips. And this actually allows us to scale up the application field as well, because in this way, we can apply it in many fields. And because we have this sensor, it's also a universal platform. So we already started to apply this in smart farming, but also along process lines in the Internet of Things. But what we want to do in the future as well is that we want to include this in the next generation of applications. So for example, in your home appliances, or also in smartphones and in wearables, because that's what this meeting is about today. So we also have this technology, and we want to also be able to use this, for example, to determine the hydration level or biomarkers as well. So that's what we're here for today. And we actually have products that can already help with this. So our sensor is integrated in an OEM solution. This is an electronic board that you can plug and play directly. You can connect it via USB device to your PC. And we have also it integrated in what we call our SpectraPod. And these are development kits that actually allow you to perform the full prediction. So for example, if you want to determine the hydration level, you can train it based on the measurements with this spectra plot. So it has the light source integrated, it's a handheld device, and it really allows you for a proof of concept. And in order to simplify this, we also have the cloud solutions, because of course you need to do the prediction models. And in order to actually do this prediction, we also have this option here. So what we are looking for now is that we want to make the invisible world visible for everyone. And here within Epic, we're also looking for partners to integrate our solution and to join our spectral evolution there. So thank you.
Thank you, Kelly. That's indeed very exciting what you have there. And let's see if I have any questions in the room. Please raise your hands. In the meantime, yeah, let me ask you to highlight again. So in what frameworks can you offer support to the others, or maybe demonstrators, and what can the others do?
Yeah, so yeah, we have a technology, a sensor technology that operates in the near infrared, and we are looking for applications for this. So also in the wearables, we are not the experts on that field yet, but we of course can provide the technology to make it also possible to use it for health applications. So that's what we're looking for.
Okay, that's pretty clear. Anyone else? Okay, Tom from CPI.
I think it's a slow afternoon, Ivan, so I thought I'd maybe help with a question. Hi, Kaylee. Could you say something about the bandwidth which is available for the spectrometer and the number of different package types? So I think for the people interested in the hardware of the wearables, we're always interested in how compact the package is and how we can mount it into the device, and also something a little bit more about the performance of the spectrometer. Thank you.
Yeah, so that's a very good question. So the operation wavelength range is from 850 till 1700 nanometer. And actually we have 16 channels that cover this full range. So it's not distinct channels, but we really cover the full range there. Then in addition to that, the sensor itself is only 1.5 by 1.5 millimeter. So this is very small. Of course, we have it now packaged on a chip carrier, as you see here also on the back. And we have it integrated on an electronics board. But we understand that that electronics board is not suitable yet for integration in wearables. So we're also working on scaling that down, for example, working on ASICs, implementation of the electronics there. So that's really shrinking down the size so that it's actually compatible with the wearables. Does that answer your question?
It does, thank you. Maybe just one follow-up one. That was, what is the power consumption currently for the device?
Actually, it's very low because you don't need to apply a voltage in order to operate it. So it works at 0 voltage. So yeah, I'm not sure about the exact value, but I know you don't need any cooling, you don't need any power consumption to read it out. So it's sufficient to connect it, for example, via the USB to power it via your laptop. That's sufficient for the power consumption. You don't need an external battery for that.
Okay, yeah, I think that answers the question. Wilfred?
Yes, I have 2 questions, if I may. So the first one is related to the packaging that from the previous follow-up from the previous question. So what do you need to get it smaller? So you might know we do micro optics, so maybe we can discuss to implement some optics into your chip. And the second question is, for that wavelength range, aren't you limited to certain chemical footprints or fingerprints better, or is it, or are you also looking at other wavelengths in the future?
Yeah, so regarding the first question, I actually think that the optics is not a limiting factor at this point because the sensor operates in free space. So that means that it's actually also, you don't need to have, for example, waveguide coupling or fiber coupling in order to make it work. And this is perfect if you want to measure in real life applications. So I think really the electronics is the first part that needs to shrink down in order to make it compatible with the wearables. And then the second question, of course, if you go to higher wavelengths, for example, up to 2.3 micron, you will reach more application fields. And that is possible also within our technology. We need to change some material because now it's InGaAs based to make it work till 1700, but you can adjust this in order to also extend the wavelength range there.
Okay, thank you. Thank you very much.
Yeah, thank you.
Okay, thanks everyone. Thanks, Kaylee. So I encourage you to reach out to Kaylee after if you have something in mind to work together. And with this, I'd like to invite the next speaker. That is a founder of the Xpanceo company, Valentin Volkov, who will talk about the low-dimensional materials for advanced biosensing applications.
Yeah, thank you very much. Let me share the screen.
Until now, we heard mostly about the wearables that you wear on your skin. And now we'll hear about something that in the eye.
Well, thank you very much. Can you see it?
Yeah, just put it in a full screen and Florian.
Because I can't see it somehow. It's
yeah, we see it, but just F5 and then it goes in full screen.
Okay, just a moment. Okay, let's make it. Now it's gone, right?
Yes.
Okay, let me try one more time and then like that. Okay, does it? Okay, it's coming.
Oh, yeah, now it's full screen, just not the first slide though.
Yeah, that's a bit strange. Okay. Okay, here we are. Thanks a lot. That's I would like to thank organizers for this great opportunity. I will talk a bit about low-dimensional materials and how it can be used for wearable applications in general. Of course, I will also, in the end of my presentations, make a focus on the biosensing applications. But my name is Valentin, and by my first profession, I'm a physicist, and for the last 20 years, I've been working in different universities, mainly as a university professor. So, but approximately 1 year ago, together with my partner, we launched the company, which is called Xpanceo. And the company is developing next generation of the electronic wearable devices. Basically, we are trying to develop, let's say, next computing category. So if we imagine that that's the line where we're coming from, first computers, then we are going through laptop to mobile phones, which are also small computers, and then an inevitable question: what would be the next? And we believe that the next device will be, of course, a wearable one, and also a device which will provide the user with our augmented or extended reality possibilities. And that's a very popular and hot topic right now, and plenty of companies are trying to develop some products. I mean, I already have lots of products, but we still believe that those products that are now available on the market, they are kind of bad gadgets. So glasses, helmets, and others, even though they work pretty well, they are not comfortable to some extent. It's difficult to imagine how to use all those bulky helms in a everyday life. So my son has this kind of helmet, and he was so excited when I bought this helmet to him. And then he was playing for a few days, and then he dropped it somewhere now, and it just collects dust, and he's still playing old-fashioned computer games. So they're kind of not comfortable. And we kind of trying to answer the question how and what kind of things should be incorporated in this device in order to make it perfect wearable device the next generation. So it should be functionality, of course. Would be, of course, nice to have all your gadgets which you use on the everyday scale in one unlimited screen, which is always with you. Then, of course, it's a form factor. That's what we say, best device is no device. So it should be something very private, weightless, wearable, of course. And then would be nice that if such a device would be good for health. So it will improve your eyesight instead of damaging it. And here is the idea of our product. It's a smart contact lens, which we kind of trying to develop right now. Again, I should admit that the company is very young. We are less than 1 year, basically. We just managed to close the first round of funding. So, but nevertheless, we have some ideas. So what this lens can provide to a user. Oh, sorry. So it's, of course, it's a seamless eye experience. It will merge the physical and imaginary world, let's say. Then, of course, there will be some health sensing system, some sensors, which will be integrated in such a lens. And then, of course, it will, this lens will give you some supervision abilities like night vision, zoom, and so on and so on. I don't know how much of those things we will be able to deliver in the end, but at least we have roadmap. And for this year and next year, we are working on a so-called supervision lens. Basically, our main target is to make a lens which would improve your vision during the night period, so like a night vision lens. Then simultaneously with that, we are developing different sensors that can be integrated on the lens, and that's what I will talk a bit today. Then also it's a holographic projector which will be integrated into the lens, and then in 2026 we actually are going to combine all these things in one perfect device. Regarding our sensors, which are integrated on our lens. Right now, we're actually trying to develop kind of universal sensor platform, which can be integrated onto the lens, and then developing, depending on the materials that is used. It can be a kind of, can be used for different purposes, for different functionalization. All in all, right now we are kind of the main design which we are developing. It's working on a reflection way. So you are wearing the lens with sensors into your eye. Then there is an outside device which sends the light in. Then we collect the reflected radiation, and then we use we use some approach to analyze the reflected light in order to estimate different biochemical characteristics of your eye liquid. So the idea is that device can be implemented as either as a stationary one, suitable for special places like hospital, for example, or it can be a mobile device for personal use, which you can use at home at the everyday basis. And then, of course, the user is supposed to use it on a normal way, like everyday scale, or every week, every month scale as usual contact lenses. Then, of course, it gives some benefits, like you can do instant measurements of many parameters. It's supposed to be relatively simple in use device, and then we hope it will give a high accuracy of the measurements. And the next few slides, I will, Ivan, how much time do I have?
Yeah, you still have a few minutes, go ahead.
What? Okay.
You still have time, go ahead.
Okay, again, the majority of our R&D team, they are traditional academical scientists, and we kind of develop our product on the basis of our scientific achievements. We still actually have a small research center within a company. It's called Emerging Technologies Research Centers, where we're actually also doing traditional academic research with the purpose of publish a sensor platform, which we are developing right now, is based on one of our recent publications, Chacom recently, and called the topographical phase singularity in atomically thin high refractive index materials. And we believe that this low dimensional high refractive index materials, this is the basis for the this very efficient and compact sensors, which can be integrated in our product. And the general problem of let's say 2D flat optics in general, 2D materials, it's a very popular topic for the last at least 10 years. And they are to some extent already revolutionized many areas on the modern physics. Also, optics is not an exclusion out of that, and scientists all around the world are actually trying to use low-dimensional materials to make highly compact and highly integrated optical components and devices. And the main problem with two-dimensional materials, it's the efficiency of such devices on the impact to the face is very low, just because the thickness of such materials is almost negligible. So the light doesn't have time to accumulate the phase change when it goes through it. And the traditional way to kind of overcome this problem is to consider the phase changes due to the, for example, reflection, transmission, or scattering when the zero reflection happens. That's well known in physics, for example, from Brewster phenomena, where once you get this phenomena where you achieve the zero reflection at the interface, the phase actually experience a strong jump. And that's what one can also do. That's what we actually try to do in our research. We kind of integrated our two-dimensional materials with a Fabry-Perot resonator. It's a simple one, like a silicon CO2 substrate standard one. Then we covered it with a two-dimensional material, and then you have this simple heterostructure. And then for particular wavelengths and polarization and angle of incidence, you can always achieve a point, depending on the plane with these parameters, where there will be always a zero reflection at a particular point. Changing the angle, changing the wavelengths, you can create a total surface of those zero reflections. And then, of course, then at the same graph, you can also print your dispersion curve of your material, which will be like a spiral one. And then the points where your dispersion will intersect the zero reflection would give you the points of zero reflection for your material and for your heterostructure. And the interesting thing is that at this point, the phase is not really determined. Basically, it's a phase singularity there just because the amplitude is going to zero. So once you are kind of playing around these points, you can easily achieve a high jump in phase. Basically, it's if you are just moving around that point in a 2D space, you will achieve a 2 pi change of phase. And plus to this point, their topology, they are satisfied with Jordan's theorem, so they're topologically protected. It means that once you introduce some imperfections to your material, the 0 point of reflection is still there. And we kind of played for different materials with this phenomena and found that it's depending on the thickness, depending on a real and imaginary part of your dielectric function, you can always create those topologically protected zero reflection points. And why they're good? Because that actually opens a possibility for manipulation with space at the, let's say, two-dimensional scale. So this is good for doing actually holography. This is doing for making biosensors. It's kind of like, at least this is a very useful phenomenon, because it seems like it's a universal platform which allows to achieve high efficiency of phase manipulation at the real nanoscale. So, and we used this phenomena to make a first prototype of our biosensor. So exactly these three-layer materials with a light beam illuminated at different angles. And then we could see that spectral sensitivity in terms of change of the refractive index at the output side of this sensor is not good for amplitude. So it's a very moderate one. But at the same moment, if we play, and this is clear, this because this is topologically protected in terms of amplitude as well. But once we are going to the phase, then you can immediately see that in terms of phase sensitivity, it's huge. It works like a very sensitive and very robust sensor. So basically, we got the sensitivity at the level of 7.5, 10 in 4th degrees per refractive index unit, which is actually better than results achieved for most advanced and most sensitive plasmonic sensors, which kind of champions in a world of sensor technology right now. So, and then we also checked and figured out that it's a very robust, very stable. It's easily scalable, cheap, easy to use, and easy to fabricate as well. So I'm running to the end of my presentation. We are very much open for partnership with everyone who is interested in, first of all, in the production of new components. We are interested in components manufacturers of sensors, waveguides, light sources, detectors, and so on. Then, of course, it's a consumer electronics companies and AR-driven software companies and platforms. And thank you for your attention. We'll be happy to answer your questions.
Okay, thank you, Valentin. Great talk, very encouraging. And let's see if we have any questions in the room. Please raise your hands. In the meantime, I'll just ask you to repeat. So the product you have in mind is the contact lens, or
yes,
you consider other types of wearables?
No, it's right now our main product is a contact lens. So we are trying to integrate our optoelectronic components at the inside contact lens.
Okay. And do you have any estimation for the size of the rigid chips that you can fit inside?
Well, yeah, it's a good question, but we are not. You mean like a computing unit which we are going to integrate or not? Yeah, we will just use those the smallest ones that are available on the market. So we are not going to develop our own. So we will just focus within the areas of our expertise. So we are playing with the optoelectronic devices, and then we will use the best what is available from electronics.
Okay, but roughly, what's the tolerance for the human eye to have this rigid piece?
It would be nice to have it with. I mean, tens of microns is good, hundreds of microns good. Everything which is around 1 millimeter is already. I mean, thick, 1 millimeter thick. It's already too thick. So it's kind of a challenge. Yeah.
Okay, so let's say hundreds of millimeters.
Yes, micrometers, because I mean it's in the end all those things they should be encapsulated inside the lens. So it's not good to put them just on the surface, because then it's too vulnerable for the outside world. It's easy to destroy.
All right. I see there is a question from Anton from EV Group.
Yes. So, and the question is, in the beginning of the talk, you mentioned that you want to enable the night vision for the people, supervision. Does it mean that you also want to integrate the LED display there in the lens?
Yes, one day. And you know, there is a company called Vision.
Yeah.
They did try to do so. To some extent, we are now trying to go on their footsteps just by using more advanced materials and kind of. I mean, we believe one can do it more compact because they use kind of a classical optical telescopic system in their projector. So we believe with the use of low dimensional materials, metamaterials, we can significantly decrease the size of the projector.
Okay, so basically, you can make the lens thinner that they did.
Yes. At least theoretically, it seems possible.
Nice.
Yeah, that sounds very encouraging. Anyone else has a question? Because I know Anton also did ask this question for a reason, because he's giving the next presentation. And so if there's no more questions, we thank Valentin again. So please feel free to reach out to him during using the contacts on the screen. And now Anton Alexeev will give the next presentation. He is a business developer manager at EV Group, and he will talk about the wafer bonding that enables the micro LED display revolution.
Okay,
Anton?
Great. Thank you very much for the introduction. I have to figure out how to hide the bar.
It's all good. We don't see it.
Yeah, but I see, and really, it is really distracting. Okay, I think. No. Okay. Anyways, I'll do it with the bar. Okay, so wafer bonding, the technology that is very, very much important for the micro displays that may be potentially integrated even to the lenses that we wear, as we just figured out. And EVG is a company that is doing wafer bonding and many other technologies. And if we consider the manufacturing of the micro displays, then we can see that it starts with taking the carrier wafer, and which contains CMOS electronics. Actually, this wafer doesn't contain anything, and it's just a blank wafer. And then we take the epi wafers, we transfer the epitaxial layer, we bond it with the microelectronic wafer, and debond the carrier wafer. We singulate the chips, and we have our micro LED display that we can integrate anywhere. And as you can imagine, there are a lot of steps that are involved into this process, and yeah, just a huge cloud that you can read later. But EVG can do everything from this cloud. We can do bonding, we can do nano imprint, everything that helps manufacturers to make the displays. And we are a company that manufactures the machine to make the microchips, all of them, from bonding to lithography. We have 73% market share in permanent bonding, and we are really experts there, and we want to encourage everybody to use this technology to make micro LED displays. So in general, the topic will have 5 main sub-chapters. First is micro LEDs, then which technologies are used there, and next it's the analysis of the micro LED displays manufacturing going to be shown. Finally, some demonstrators of our technologies and some unique features that we have. So as you can see here, the micro LEDs are really small. They are about 10 micrometers width, and unlike the mini LEDs, they normally come without the substrate, because these mini LEDs have a substrate under them, which makes handling of them very complicated, and making the device with them is super hard. Therefore, we don't see them yet in the mobile phones, in the phones, in the smartwatch, in the TVs, nowhere, but it will come. What are the benefits? The benefits is that micro LED display has astonishing brightness, which is approximately 1,000 times lighter than, more than the OLED, and it's actually beyond the threshold of the eye. But that means that it can be integrated in the systems with high optical loss and still be bright enough to deliver you a very contrast and colorful, vivid image. Okay, so if we speak about the micro LED displays, they normally consist of two parts. That's the LED array and the backplane. The backplane is used to drive the LED array with certain current shape in order to enable functioning of the display itself. And the LED array is just a number of the LEDs that emits the light. Together, they have to be bonded, and it's going to be the display. Why is it like this? Because normally the LED array is made of 3-5 semiconductor materials, while the backplane is CMOS. And therefore, it's intrinsic heterogeneous integration need for all of the micro LED displays. If we look at this problem from the other side, we can divide them into two main categories. First one is the direct view displays. That's something that you look with your own eyes directly. Second one is the micro displays that are used in the virtual reality or augmented reality or HUD cases. That's the displays that are hidden, and basically you see a projection of the display through some optical system. What's the difference between them? That for the normal displays, we want to manufacture this micro LED array and separate this into individual pixels, pick and place them and put them at the backplane. And then we'll have a huge distance between the pixels at the backplane. For the micro displays, we transfer everything as one monolithic thing, which makes the pixel density extremely high. And also the size of this display becomes extremely tight, which can fit inside of the optical systems like your wearable goggles. Okay, so if we go and analyze how these displays are made, there are two main approaches. One is the hybridization, second one is monolithic approach. In a nutshell, in a hybridization, we first take the compound semiconductor wafer with epi layer, we process everything into individual LEDs, and then we transfer these LEDs at the CMOS backplane. This is decent process, but the pitch beyond 10 micrometers is really limited, and this pitch is required by all the AR applications. We can make something in between the hybridization and monolithic, which works like this. We take the compound semiconductor wafer, and then we transfer the epi layer to the CMOS, and then we do processing directly on the CMOS wafer. By this way, we can achieve, not we, but our customers can achieve the pitch of the pixels up to 1 micrometer nowadays. And there are certain ways of manufacturing that are currently under development, which are purely monolithic when you grow the epi layer on a CMOS wafer or control circuits on the epi layer, but it's all R&D phase, and because of a lot of intrinsic limitations of the process, this is not feasible yet. So we concentrate on these two in our company. Here are some examples of how to manufacture a micro LED array, and I will not go in details. You can check it in the slides later because it's a lot of information here. But if we consider the technologies required for different cases, it's always the thin layer transfer, and because you want to for efficient HVM, you want to scale up from the small epi wafers that are normally up to 8-inch to 12-inch CMOS wafers. That's adhesive bonding because you want to carry these tiny layers of the epitaxial layer. Then it's laser lift-off to get rid of the carrier of the epi layer. And of course, technologies like metal bonding or hybrid bonding that enable very precise contact matching with high pitch accuracy. Our company can do it all. Okay, and then if we discuss which pitch of the pixels is feasible with different methods, we can separate bonding into 3 main categories, which is no interlayer bonding, which consists of fusion and hybrid bonding. In these cases, with this, the most advantage, the most powerful bonding technique, we can achieve pitches of down to 2 microns. Metal interlayer can enable the 5-micron pitch with thermal compression and 30 micron with transition liquid phase or solder-based bonding. And finally, the bonding with insulating layer can enable like 30 micron pitch as well. And here are some examples of what can be achieved with these methods. And of course, the most interesting are hybrid and fusion, because that's really, really the state of the art nowadays. But what makes EVG unique and what we can do that is really demanded by the customers that develop these micro LED displays nowadays are the following technologies. First of all, we have COM-bond, and that's the device that can achieve bonding of the wafers in the vacuum. And it's oxide-free bonding, so there is no oxide growth at the interface. It has high precision alignment in the vacuum, and it's very great for the process development phase because we don't have this oxide layer and we can really experiment. And COM-bond can bond anything with anything, almost. And here you have different combinations of materials that are possible to come to bond there. Some microscope images of the interface, how it looks like. And we are working on expanding the list of the materials that are tested to be bondable. And of course, you're more than welcome to send the wafers to us, and we will use our heterogeneous integration center to check if the process is suitable for you. Next thing that we can do die-to-wafer bonding, and it's a crucial technology for making the scaling up the small epi wafers from 8-inch to 12-inch, and then using the whole economical power of the large semiconductor fabs to manufacture the backplane. And die-to-wafer bonding has extremely great results. You can see that the interface quality is basically not distinguishable from the wafer-to-wafer bonding. Next, what we can do, which is extremely good for all the development applications, is we can bond wafers of different size together with high precision. For example, here you can see different combinations of the wafers bonded together. And on top, you can see that we can do it up to 50 nanometer alignment accuracy, which of course dependent on your wafers. And this number is given for silicon to silicon, different substrates. And it may deteriorate if we use 3-5 semiconductor wafers, but it's all up to be tested for each certain case. But so far we achieved 200 nanometers 3 sigma value for alignment for overlay between two wafers for silicon to 3-5 semiconductor wafer of different sizes. And if you go next technology is nanocleave. It's a very brand new technology that we developed in-house. That's basically technology that enables debonding of the carrier wafer with extreme precision. And the technology is basically an inorganic layer that is placed between the device and the carrier. And this layer can be activated with the infrared laser, and then the debonding happens. The benefit of it is that it can be done directly through the silicon wafer, which enables silicon wafers to be carriers. And that's great because if we want to have something similar, might be a glass wafer, but glass wafers are not very much suitable for the handling because they're fragile and semiconductor industry doesn't like them. Moreover, this layer is extremely thin and it's stable at a very high temperature, up to 1000 degrees. Finally, let's make it epic. And we have competence centers in our headquarters in Austria, where you can send the wafers and we can develop processes and bond the wafers for you. And you can test our equipment and get extremely good results. So if there are further questions, I can answer them.
All right, I think that was epic enough. And thank you, Anton. Let's see if there is a question in the room. In the meantime, maybe I ask you to repeat, speaking of the micro LED screens, what is roughly the power consumption level relative to OLEDs or?
Well, the power consumption level depends on how much you drive it. But so far, if you speak about, so the issue that the efficiency of the micro LED is really dependent on the size of it. So the smaller it gets, the less efficient it is. if we speak about micro LEDs that are about 5 micrometer size, we are in the same range of the efficiency that the OLED is. Depending on the color, it slightly varies, but more or less it's the same efficiency as for OLED. Yet, at these, the micro LEDs can be driven with currents that are 1,000 times higher than the OLEDs. Therefore, comparing to a similar OLED micro LED display, the power, the thermal power would be 1,000 times more, with the benefit of having 1,000 times higher brightness for this size. If we go for micro LEDs with higher sizes, then of course we start to gain the advantage over the OLED technology.
Okay, yeah, that's clear.
And yeah, it's very important to know that that's very much developing trend, the micro LED usage, and the efficiency is being increased at tremendous speed nowadays. So maybe in 1 year, this data already not relevant, and the micro LEDs are shown to be way more efficient.
All right. Question from Badhise from CEA-Leti.
Okay, thank you for this talk. I have a question regarding the die-to-wafer bonding technique. And
yep.
In particular, I would like to know if you have a specific procedure or equipment regarding the collective surface preparation and the die inspection before bonding.
Yeah, so we have equipment for preparation of the dies. Basically, the equipment can take the carrier wafer with dies placed on it. It can activate all the dies, okay, so they are ready to be bonded, and it also can clean them.
Okay.
Moreover, you can, yes.
Okay. I'm sorry. You have a specific, for example, one of the interests of this technique is to also to have the possibility for die inspection and to remove a bad die, or to put instead a good die with the good surface. I would say with no defect and so on, because we know that one defect can be detrimental for the bonding.
Yes.
Okay, so you have a pick and place technique, which is so you can guarantee yes, a very high yield with the bonding technique thanks to the die selection.
Yes, exactly. Yeah, because we can our customers can pre-select the good dies. They can place only the good dies at the wafer, and therefore this collective die-to-wafer technology actually takes the best of the two worlds. It has the cleanness of the wafer-to-wafer bonding and the selectivity of die-to-wafer bonding, where only pre-tested dies can be used. Yeah, thank you. It's a very good remark.
Okay, thank you.
All right, anyone else? I think I'm sure this technology can be used for several sensors that we heard about earlier today.
Yes, yes. Basically, any integration of 3-5 materials or any other materials with silicon wafers is enabled by bonding. So contact us. We can develop something for you.
Yes, this technology is a real enabler. Well, okay, thank you, Anton. Then with this, we will switch to the last presentation of the day. And it's also about the enabling technology and, well, actually more on the material side for wearables. So the last speaker is Florian Jung, Global Business Manager at Sabic, and he will talk about the resins used in optical lenses.
Hello, everyone. Can you confirm you see my screen?
Yes, the floor is yours.
Okay, perfect. Thank you, and thank you for having me. So I'm Florian Jung. I'm the Global Business Manager at Sabic. I will come back to Sabic as a company and what we do in a second for those who don't know us. But based on everything I heard and feedback that we got from our customers recently, we would like to start with some kind of an hypothesis on why we want to do this presentation. And that hypothesis is that with the increased functionality of wearables and the required integration of sensors or multiple sensors in one device, there might be some challenges coming with them. And in Sabic, we are a supplier of thermoplastic resins that are used in optical lenses. And we are here to help you to solve some of these potential challenges you might have. So let's look at these challenges and go through a few of them. So many of our customers are seeking for options, and I also heard that today, to reduce packaging size, right? Space is getting smaller and smaller, and these devices, functions are added as we go more and more, and restricted space seems to be a challenge, especially also in combination with optical elements and lenses that need to pass reflow soldering processes at 260 degrees C. The second topic that we hear very often from our customers is that they need maximum scalability. So we have customers asking us on how we can help them to do, let's say, 100 million pieces a year. So for sensor applications that are significant, and with wearables becoming more and more dominant in the market, we assume that these level of parts or these numbers of parts will be realistic pretty soon for some of these wearables and the sensor elements being used in these devices. And last but not least, design freedom and function integration are more and more getting critical, because you cannot have a separate part for each of these, or a separate part for each sensor or each function. So how can you integrate several functions into one part to make assembly easier, to make it cheaper, and also more reliable in application? So question might now be, how can Sabic as a resin supplier help you to increase your build rates, ease up your design, and simplify your assembly? Looking at that, there's different buckets I would like to cover. One is processing. If you take thermoplastic resins, you can utilize micro-injection molding. The advantage of that technology, for those that are not aware, are, first of all, you're extremely flexible in your design. You have very high design freedom. The second topic is you produce multiple pieces in one shot just within a few seconds. And that's just needed if you want to have these high quantities we were talking about earlier. You need to have a process that's very fast, that's very reliable, that's highly automated, and does produce many pieces in one time. The second reason why we believe we can be of value for this supply chain is our development support that we're offering. Because we do not only develop these resins that fit industry needs, but we also have a global network of partners across that supply chain of starting with the design of such an optical element until developing a mold that can actually manufacture it, setting up that molding process, but also covering the whole secondary operations part, doing reflow soldering testing on an industrial scale, reflow soldering often, support with assembly processes. So which adhesive, for example, is best suited for these different materials? This is one question that we are asked very often. And in order to give you that best possible support as a resin supplier, we have integrated R&D centers focusing on these optical solutions globally in different regions, and can help to support locally depending on where the support is needed. Last but not least, Sabic has a global footprint. Many people don't know Sabic, but Sabic is the second biggest chemical company in the world. We actually employ 30,000 or more than 30,000 employees today, and have 66 locations around the world. So we certainly have both the expertise, but also the scale to support what is needed to support developing new applications with our customers. So just a quick view on why we believe that the materials we are developing ultimately are interesting and well suited for this application space. First of all, there's two main families, I would call them, I would like to differentiate between. One is what we call Ultem. That's a material that's very dimensionally stable, but has a heat resistance up to 200 degrees C. So you can use it for any application you don't need reflow soldering at 260. You cannot use it for 260 reflow soldering. If you need that, you have to move to the Xtem family, which is a different polymer. and that resin will be able to withstand refill soldering without significant deformation or change in optical properties, which is unique for thermoplastic resins. Obviously, the main topic besides temperature resistance is transparency. We have a very good transparency in the near infrared area, in between 850 to let's say 1500 nanometers. The natural materials have a transparency, as you see on the left, at 1 millimeter, depending on the grade, from 88 to 87%. But we do have the possibility, and do that frequently for our customers, to actually put an anti-reflective coating on top of our lenses after molding, which does increase the transmission rate of our resins above 90% across that range of 850 to 1400 nanometers, and therefore is very, very suited also to be used for detection of biomarkers, for example, that have been covered in the presentation just before. And with that, I believe there's no excuses not to contact us if you have one or more of these needs that we have been covering. We are more than happy to have a discussion with you. My technical expert colleagues and I are here, and we kindly ask you to reach out at any point of time, and we will be happy to have a conversation with you. Thank you.
Yeah, thank you, Florian. Very interesting talk. I think it will be interested for several wearable devices. Let's see if there's any question in the room so far. Can you, Florian, actually speculate a little bit on the particular applications for the wearables of this plastic molds and the optics?
You can imagine any application where you need an optical sensor that collimates, or transmits or receives light for an application in that near infrared band from 850 to 1350, or in some cases 1500 nanometers. So no specific application space, but a wide range of possibilities and applications that we are utilizing.
Okay, and you also mentioned, so you are used to work in the hundreds of thousands of units. However, for a smaller scale, more development type of applications, is that also suitable?
Yeah, that's a good point, and I should have covered that. Usually what you see is that customers start with what we would call a prototyping mode. So the surface of that mode would obviously be needed to be as good as possible, but you don't need to have the possibility to produce with that same mode millions of pieces. So there is possibilities to make, also you don't need multi-cavity usually at the beginning, but one cavity is good enough. So there is possibilities to do a few hundred of pieces, for example, or even less for development stage, and that has been done before, yes.
Okay. So you're located in the Netherlands, correct? So you can be reached out easily in Europe.
The European headquarters is Netherlands, that's correct, and we have contacts around the world. No matter where you want to go, you will find somebody working and supporting us.
Okay,
yeah.
That's very good to know.
Members and I'm more than happy to also see our facility face to face. So if anyone is around, our facility in the Netherlands is based in Bergen-op-Zoom, down in the south of the Netherlands. You are more than happy to get a tour.
Okay. Yeah. Let me put you in contact after with our colleagues from TNO and MantiSpectra. I think that could be an interesting collaboration right there. So if there is no further question, I think this is good for today, and we're also just about to hit the 5 p.m. Threshold. So thank you again to all the speakers of today. That was a really interesting and a very active participation actually from all the audience. So now you have this standard poll to give us some feedback on what you saw today. So please fill it in. In the meantime, let me just briefly share a few closing notes with you. So this was the EPIC Online Technology meeting on photonics for wearables for you. And today we had the privilege to hear 7 very exciting presentations from EPIC members such as CEA-Leti, Rockley Photonics, TNO, MantiSpectra, Xpanceo, EV Group, and Sabic. And thanks again for everyone who was present today. Also, let me mention that this was provided to you by all the EPIC team. We're here to support you for technology and marketing and everything else you need to develop business in photonics. And this was one of the last ones, online meetings we have today before the summer vacations. However, I invite you already to follow us starting from September. We have several upcoming physical events which cover the topics of photonics for defense, photonics for space, photonics for bio and life science applications, as well as industrial quantum photonics and microelectronics and photonics. We'll also follow up with online meetings on hybrid photonic integration, optical metrology solutions for industry, optical design and simulations, and new mid-IR developments for novel industrial manufacturing. So make sure you don't miss the dates. And thank you for being with us today. Goodbye.
Bye-bye.
Bye-bye. Thank you.
Bye. Thank you.
Thank you. Goodbye.
Thank you.
Bye.
Thanks. Bye-bye.
Bye-bye.
Thank you everyone for joining. Yes, so at this
Bye-bye.
point, the official part is over.